Welcome, everybody, to the first meeting of calendar year 2025. I am Waltz Treybergs, your duly elected MAS president. Welcome you all here in the first cold day of the year. So what I want to do is, first off, let's do this. Getting used to this. So the agenda for the meeting, we'll have some welcomes and introduce the new board and say something from the outgoing board as well. Trina is here and she will have a few words to say. Get a membership update as usual. The next thing we're going to do, we're not going to do the treasurer's report like we normally have. We are going to have our audit committee do a report. So Alan Touchberry is going to do several slides and answer questions about some of the financial investigations that we've internally audited and come up with. I'll go through some Astro events, some upcoming MAS events, and then Suresh is going to do a presentation about Comet Tsuchinchan Atlas. So that'll be a great presentation. And then we'll have some other announcements. Jerry's going to do some AL awards. And then we have some announcements from the NCRAL on their upcoming convention here in the Twin Cities. And then we'll have our featured speaker, Dave Falkner, talking about the cosmic ladder. All right. So the MAS board, we are all here. I believe we are all here. I am the president. John Zimmich, the vice president. Claire Weaverling, secretary. Jesse Palmer, board member at large, and Phil Ramsey, board member at large. So stand up, please. Now, we did make one change because of our bylaws and the term limit clauses in the bylaws. We did make a change at treasurer. So I would like to announce Noha Reda as our new treasurer going forward. So she has been appointed to complete the term for 2025, and then we will have the treasurer term will be up for election in December. So welcome new board members, and we're eager to roll up our sleeves and get to work. So outgoing board, many thanks to Trina, our beloved president, over the last 2 years. Ahmed Reda has been the board member at large for the last couple of years. Dave Falkner has been secretary the last few years. He's been president. He's been probably every single term here. And then Matt Dunham, our former treasurer, also 6 years of good work as treasurer for that. So I know that Trina has a few words that she wants to say. So Trina, come on.
You think?
Oh, I think. Oh, hello. That is very sensitive. I just want to say thank you so much to everybody who is in the MAS, who volunteers, who is on the board, who went through all the changes, from being Mark as president to, handling me as secretary, and then 2 years of presidency. I added it up, and that's 72 months and 144 meetings for my 6 years of being on the board. So not doing this is really strange to me. But I do know that you are in good hands. And I just want to say thank you to everybody who's been supporting us and contributing and volunteering, and just appreciate it very much. So it's all for you, Waltz.
All right. Thank you. Okay, members, we got a bunch of new members listed up here on the screen. Are there any new members with us in the audience today or online on Zoom? If so, please raise your hand. Can you stand up and just state your name? Hi, Ken. Welcome to MAS. Is there... Also, from a summary, Steve gave us the report a couple days ago. So we have 738 total members. 3 honorary, 100. Oh, Jacob's online. Welcome, Jacob, as well. We have 738 members. Oh, excellent. 159 patron, 542 regular, and 34 student members. All right, thanks. The MAS is because of our membership, and active participation is encouraged. Everybody, please volunteer. We've got so much work to do. There are so many jobs to do all around the whole MAS, whether it's running the sites, whether it's doing administrative stuff, doing website stuff, doing membership stuff, all kinds of different jobs, designing logos, doing accounting, doing the books, doing all of that stuff, all the board member duties, all of the taxes, all of that. That's all done on a volunteer basis, and we always need more volunteers. Site committees always need more volunteers, more key holders, more people to do outreach, everything just like that. So the more people, the better. And we've got 738 people total in our club, and we've got a deep pool of people that hopefully can step up and help us out.
Training at sites.
Okay, key holder training at sites. So the best place to do is visit the site areas of the website. So if you go to the facilities area on the website, should be a link to key holder training. And if it hasn't been published already in the calendar, the key holder training schedules have not been published yet to the calendar, but will be before the operation season opens. All right, Astro events. A few things happening in January. Right now, the Quadrantes meteor shower, if clouds ever go away. January 4th, lunar occultation of Saturn. January 10th, Venus will be at its greatest elongation. We saw Venus popping through the clouds on the way from the restaurant to here. So it's there, it's pretty high up. Venus will be full half phase dichotomy on January 11th. So pretty much like in the second picture there. Full moon, January 13th. There will be a lunar occultation of Mars, January 13th, at the same time as C2024 G3 Atlas, but I think Suresh might mention it. That's not really going to be visible from here at all. So not here, as Dave would say. Mars is at opposition, January 16th. So definitely get out that. This picture here is one of my pictures taken from J.J. Casby, last Mars apparition opposition. So definitely get out and see Mars. So if the clouds cooperate. New moon then January 29th. But there's some cool upcoming space missions. So there's two CLIPS missions, NASA CLIPS missions going to the moon, potentially launching this month, the Lunar Trailblazer and the Blue Ghost. So there's two Falcon 9 launches going to the moon. Blue Origin's New Glenn rocket is scheduled to test Sunday. Chris, what time? Sunday evening. So that's potentially, they could have their first test flight of the New Glenn this Sunday evening. And then in a week or so, Starship Flight 7, Test Flight 7 is also expected to go from Texas. So pretty exciting from a space launch standpoint. All right. BSIG, Suresh, you want to come up here? So in the winter, typically in the summertime, we have observing sessions, but in the winter, Suresh arranges a bunch of really cool presentations. So Suresh can talk about the next presentation coming up, and then right after that, you can launch right into your talk.
Great, thanks guys. For the January BSIG, the Beginner Special Interest Group, Bob King is going to present for us again. Bob always does a really good job, and this time he's going to do understanding, forecasting, and photographing the Northern Lights. This is his synopsis. We'll look at what causes the aurora, how to get alerts so you don't miss a great show, and easy ways to photograph them. I don't know if you're Facebook friends with Bob King. It seems like everybody is. But if you go on there, it's wall-to-wall aurora pictures. It's like he gets them every night up in Duluth. And so if you ever want to get alerted by that, Bob's website or Facebook site is a really good place to go. 'Cause he'll see them before anybody else usually. So he'll do a good job for us. The presentation will be on Saturday, January 11th at 1 p.m. The Zoom link is on the MAS website. And if anybody has any questions, they can reach out to me. So let's see. like that. Backwards. Can we turn the lights down a little bit? So, so this is just a kind of a synopsis or I guess a summary of the recent apparition of Comet 2023 A3 Suchichan Atlas. For clarity, I'll just say 2023 A3 going forward because I can't say Suchichan very well. But it was one of the best comets we've had for Northern Hemisphere viewers in a generation. It really was, and it kind of it kind of felt like it flew under the radar a little bit with the astronomy community. I think because the media is kind of afraid of hyping up comets, given what's happened historically. So, let's see, Vault. Oh yeah, Vault. How do I go back? How do I go down? That's the one on the right.
One on the right is forward.
That one or that one? Okay, there you go.
There.
Perfect.
Yep.
Thanks. So let's see. There we go. Can everybody see it okay? All right. All right. So just wanted to start off with some key dates for this comet. It was discovered on January 9th of 2023 by the Suchichan or Purple Mountain Observatory, which is located in China near Nanjing. At the time, it was magnitude 18.7, so really, really faint, but it was still 752 miles away, so nearly to the orbit of Saturn when it was discovered. But information from that observatory was slow coming out, so I couldn't really pin down when the discovery notice actually went out. So on February 22nd, about a month and a half later, astronomers affiliated with the Atlas program in South Africa also discovered this comet. And at that time, it was about 680 million miles from the sun. And their notice went out, and then all of a sudden the Chinese one came out. So the Astronomical Union decided to give them both credit. So if you guys don't know, the Atlas program is an asteroid. Basically, they're looking for asteroids that have a potential for hitting the Earth. So they're constantly monitoring the sky, and they've got telescopes, two telescopes in Hawaii, one in Chile, and one in South Africa. So they pick up comets all the time in their work. So this is another example. So again, at the time that discovery in February was still like 17th magnitude. And so we were kind of waiting for it to brighten enough for amateurs to get involved. And by May of this year, the comet finally reached 10th magnitude, and amateur astronomers could start to really monitor this well. And that's when I found it for the first time. And then another important thing here is with comets, we never know if they're going to survive, especially when they come close to the sun. And this comet, I mean, if you read the reports from earlier this year, they're giving about a 50-50 chance of surviving its close approach. And what made it worse is that the orbital geometry made it so that the comet would not be visible from Earth from about the second week of August or so till the end of September. So we're kind of in this blackout period. So we weren't sure if it would survive until after it actually passed perihelion. And then September 27th is when it reached perihelion at about 36 million miles from the sun. So pretty close to Mercury's orbit from the sun. And then late September, the comet briefly reappeared in the southern hemisphere. And I'll talk about that a little bit later. And it was at third magnitude at that time. And that's where astronomers and amateur astronomers were rejoicing because the comet actually survived. And so we were going to get a good apparition. And then the remaining dates on here, October 9th is where it reached peak magnitude at minus 4.9. So briefly, it exceeded the brightness of Venus, but there are no confirmed observations from Earth at that time because it was right in the sun's path. But we'll talk about that too. And then October 12th, that's kind of the time. October 11th and October 12th are kind of when it became visible in the Northern Hemisphere for the first time. And that's when people really started getting out to see it. And by that time, it already dimmed from minus 4.9 or so to about minus 1. So just in a couple of days, this happened. And then the best time for us really to see this, to get a nice broadside view of the comet, was October 13th through about the 22nd. It developed an anti-tail, which I'll talk about. And and a really stellar false nucleus, plus a dust tail that extended out to at least 18 degrees. Even with the moon out, we could see that. And then the rest of October, it faded rapidly, but we still got a really nice look at the tail. So let's see. So one of the other things about the comet was when it was passing in front of the sun from the Earth's perspective in early October, it happened to pass through the view of the SOHO spacecraft. SOHO is NASA and the European Space Agency's Solar and Heliospheric Observatory. And so for all intents and purposes, this was the only way we could keep an eye on the comet for about a week, around just after the perihelion time, up until people in the Northern Hemisphere could see it again around the 11th. So if you see here, that's Mercury, by the way, on the left. You see it wandering out. And then SOHO blocks the center there to do its solar work. And then the comet was literally passing right between us and the sun during this period. So I think it came in around October 7th and stayed until about October 13th. This is about 6 or so days of activity. So one of the reasons the comet got so bright was because of something called forward light scattering. And it's kind of the technical definition of forward light scattering is when you get some scattered particles or get deflected in a forward direction. That's the technical explanation. But the way I like to think about it is if you look on the upper right here, if you ever see a car coming at you in a fog, the car headlights are visible, but right when it's pointed at you, it gets really, really bright for that short time, right? That's essentially what this comet did. If you look at the picture below, on October 9th, the comet lined up directly between the sun and the Earth. And as a result, we got that tail pointed right at us, and we got this forward light scatter effect. So the comet really took off in brightness for a few hours, about half a day really, around that time. So that's what I'm trying to show here. So what are comet tails? So there are really two main kinds of comet tails. There's the ion or gas tail, and then the dust tail. The ion tail is made up primarily of very fine particles, very lightweight stuff that tends to be pushed, that the solar wind can really push along really easily. And so because of that, the ion tail tends to point in a straight line directly away from the sun from the comet. These particles are electrically charged, and they actually create a magnetosphere. So comets can have magnetospheres that will, again, point directly away from the sun. The other thing about ion tails is that as the sun's radiation ionizes the carbon monoxide particles, they can cause the ion tail to shine blue. So how many people here saw Comet Neowise in 2020? Do you guys remember that ion tail that I had, a really nice one? This comet didn't have an ion tail, or it probably did, but we couldn't see it. It was hidden behind the dust tail. So what is a dust tail? So dust tail is made up of larger bits of the comet. So think of like the dust and the ice that were actually on the comet's surface. They get blasted off by the sun's radiation and winds and stuff. And these particles, because they're heavier, they tend to trail the comet as it moves through its orbit. So as you see in the picture here, it's up on the upper right there. Let's see, where am I? So because of this, they move more slowly. They can create some really nice arcs and curves and things like that. And since these particles reflect sunlight, the dust tail usually shines either white or yellow. And the other thing about it, dust tails is as the comet crosses the Earth's orbit, if the Earth passes through that later on, comets could be the source of meteor showers here on Earth. And then finally, I'm going to talk a little bit about anti-tails. Anti-tails are really another form of dust tail. And these are even heavier particles from the comet that got blasted off. And because they're even heavier, they move even more slowly and along in the comet's orbit, and they tend to create a disk of these particles that just follow along in the comet's path, well behind it. And as the comet passes through Earth's orbital plane, we see this disk of comet particles edge on, and that creates the anti-tail. And I went back looking through my records. I think I've seen roughly 80 comets over the years. This is the first one that I've ever seen that had a real good anti-tail. So they're amazing to see. They only last for a really brief time while the comet and Earth are kind of in this alignment where this anti-tail can be seen edge on. So, like I said, the first time I had captured it, imaging wise, was in May, when the comet reached 10th magnitude. And even then, it looked really good to me in the sense that it was an active comet. It had a really strong developed coma by then, even though it was still a couple 100 million miles away. It also had a tail that was roughly a degree long by then, and you could see that it's slowly arcing there a little bit. And it had that greenish tint, which is cyanogen gas. So to me, back then, when I first saw this, I'm like, this comet has a chance of being something special, especially at that distance that was so strong. So again, we in the northern hemisphere kind of got stuck because the comet went south, and so we didn't get a chance to see it again until let's say the second week of October. So a few of us, Clayton, Don Gadzik, Nick Johnson, and I went up to Crex Meadows on October 11th to take advantage of the big hill up there, and we were able to get it. Now, mind you, on October 11th, the comet was only 12 degrees from the sun. So if you hold your fist out like this, at arm's length, that's roughly 10 degrees from here to here. So it was just that far from the sun, 12 degrees. So really close. And to be able to capture it by this, it was still really bright. I mean, it was between -1 and -2, even on October 11th. So it was really bright. 2 days later, October 13th, the comet had moved far enough away from the sun to really get a nice look at that tail. So this comet was moving away from the sun at about 4 degrees per day. So every day it got better, even as it started to fade. So this is a picture I took at ELO. The tail extended about 18 degrees, even though we had really strong moonlight that week. So I think full moon was right around the 15th or 16th, something like that. And still we could see this tail, naked eye, stretching, if you look, stick your fist out, almost 2 fists away from the comet, pointing directly away from the sun. And at this time, I think the comet was still first magnitude. It was during this week, this October, let's say October 13th through October 16th or 17th, that we get our best show for this comet. Now, you remember I talked about the anti-tail, right? Well, there it is on the upper left there. Look at that, how it points. It looks like a sword, doesn't it, coming out of the comet's head? That's what I think of it, as a straight line. And again, those are the bigger comet particles. They got blasted off the surface by the sun. And we just happen to be right edge on with that. So that's why it looks like that. The other thing I noticed about this comet was, though it had a really well-developed coma, there wasn't a lot of detail in there because it was a really active comet, so it kind of washed out a lot of detail. But it did have a strong dust tail that stretched upwards of 16, 18 degrees by that. Just by the way, on this night, it happened to pass by M5, the globular cluster, which is there on the lower left. Thanks. So this is October 20th, so 5 days after that previous shot. What do you notice about that anti-tail now? It's not pointed directly away. It's not as sharp, right? Because the comet's moving out of the Earth's orbital plane. It's moving northwards at this time. So here we see it getting more diffuse and getting fainter, but it's still visible. I mean, we could still see it naked eye. It was that bright. And the comet, by this time, the tail had shrunk a little bit down to maybe roughly 10 degrees or so from 18 just a few days earlier. And I think by the 20th, it was around 4th magnitude. So it was really dimming. I just threw this shot in because people say that you can't do real astronomy with a C-star. That was taken with a C-star. So again, this is a composite. This is 36 minutes of exposures, 10-second exposures with a C-star. But you can see, even here, you can see the comet has if you look inside the dust tail, there's a brighter tail on the upper part of that. So there was some definition within the tail. It's just a lot of it was washed out just because of how active the comet was. A couple more pictures here. Here's the 28th. It passed by a small globular cluster, NGC 6426, and I think that's an Ophiuchus. You can see the comet's a little bit fainter, you can see a little more of the definition inside, but that the tail's getting a little bit fainter. And then this is 1 day later on the 29th. This is a little bit longer exposures at 6 minutes, and this shows some of the color inherent to the comet. Remember, dust tails can be yellowish or whitish. That's what's showing here. And you can still see some of the anti-tail, but look how, on the bottom left there, but look how diffuse it is now, because it's really moving out of our plane. And then finally, on Halloween night, the 31st, as the comet was moving away from the sun, and by this time it was roughly 50 degrees away from the sun, it was moving closer to the summer Milky Way. So it was drifting in the path, getting closer and closer each night to the summer Milky Way, which is what that is there on the left. And these are the clouds that go from Scutum all the way down to Ophiuchus. So with Aquila in the middle. So just to give you some idea. So if you look online, there are a lot of really pretty pictures from around this time as it was doing this. So what are the brightest comets of the past 60 years? So this comet is technically the third best, brightest comet of the past 60 years when it got to a magnitude minus 4.9. Unfortunately, nobody saw it when it was magnitude minus 4.9. And by the time we got it, it was really -1 or 0, somewhere in that range. But still, it was a really good comet based on the last 60 years. There are several on here that have happened in the last, say, 20 years. And I want to just get a show of hands here. How many people have seen, let's say, more than one of these comets? Hale Bopp, Hyakutake, a good percentage here, probably at least 2/3 of the people here have their hands up. I counted 8 on my list. So of my personal list since the 90s, my favorite comet was Hyakutake. Who saw Hyakutake? That had a 75-degree tail. It was unbelievable. And then probably the second best one that I've seen is probably Neowise. That happened in 2020 during the COVID stuff. That one wasn't as bright as some of the other ones, but we just had a really good angle on it. So we saw a beautiful ion tail, and the way it rose and became circumpolar, so we could view it all night. It would rise in the east early on. It was like the 4th of July week. And then a week or two later, it became circumpolar. So you could see it all night long. I remember seeing it from CGO, capturing it at like 7 p.m. and following it all the way till dawn. So that was amazing. Let's see. So the ones at the top, Ikea Seki, that was a Kreutz sun grazer. And what that was is astronomers believe there was a huge comet that came through the inner solar system at some point in the last 1,000 or 2,000 years. They don't know exactly when, but it passed really close to the sun, like within 200,000 miles of the sun, and was likely disintegrated. But on the way in, it also broke into fragments. And we're still getting some of these fragments. And some of these fragments have created some of the brightest comets in recorded history. And one of them was Ikea Seki, which got almost at -10. It was visible in daytime, and it was almost as bright as the full moon. So that's crazy. McNaught, one of the things that comet people will tell you is that we never get the great ones. The Southern Hemisphere always does. And McNaught is the prime example of that. Have you guys seen pictures of McNaught? Did anybody see McNaught? Nobody. That was the second best comet of the last 60 years, and it was almost exclusively Southern Hemisphere. And then I put this one third on the list. Unfortunately, Kohoutek's on there too, and people know about Kohoutek. That's the comet that was supposed to be the comet of the century in 1973, and it wasn't that it wasn't a great comet. It still got to 0. It just wasn't the big dramatic comet that the media had built it up to be. So I have one more thing to show, if I can do this. Hey, Baltz, I can't get to my link.
Oh, that link doesn't work.
Okay, never mind. Any questions? Any questions online? All right, here you go. Thanks, guys.
Thank you, Suresh. All right. Up next is our good friend, Mr. Jerry Jones. Jerry has a ton of, grab the microphone, Jerry.
Thank you. Good evening, everyone. I have a ton. This is great. I haven't been here for a little while,
And you got time.
and it is delightful to be able to toss a bunch of awards this evening. And the first one is David. Come on up, David. David has received 3 awards all at the same time. The first award is the Lunar Observing Certificate. And along with, when you do everything, not only do you get the lunar observing certificate, you also get the lunar binocular observing certificate, and you also get the naked eye lunar observing certificate. 3 in 1. What a deal. Give us a little info about your experience.
Okay, thanks, Jerry. Well, like a lot of you, you get your telescope out kind of when it's a perfect night, and you kind of look at the same old things all the time. Making a list kind of helps, but I've been coming here for about 2 years, and I hear people get these awards, and I go look them up, and I think, oh my God, I can't possibly do that. It'd take a lifetime. And a lot of you are smiling, realizing that it isn't all that bad if you really, really want to do it and get into it. And I chose the moon for kind of the obvious reasons that it's there a little more often. And we do live in a Bortle 4 area, but there's trees and things. And so talking to Jerry, he really encouraged me back in, I think, September to go ahead and do this. And I downloaded the list. I also got the lunar book from the league, and then also the sky and telescope map. And I spent the first couple of nights just sitting in a lawn chair looking at the moon, and recognized the rabbit pounding the mochi. We kind of went through all those. I had talked to Jerry, my wife, who came along tonight, a few years back, gave me some really nice 10 by 42 binoculars, which were great for birds, okay to kind of look at the moon, but I needed something better. And that's where the second part of this, belonging to the club, really came in, was I got one of the lunar scopes. I got the 25 by 100 binoculars. And so the second step was then to do that. Getting to Anton's is really easy, assuming there's no road construction, which you couldn't assume in the summer, but he made it really simple. We explained everything. They're big and they're bulky, and I probably went through about 80% with the loaners. And then, like a lot of you, I thought I could just buy that. And ended up getting the next size down, which was the 20 by 80, which I did find a little easier to handle. You're on a tripod either way, but so it was a great to be able to look at one model, order from Amazon, caught it on sale, got the ED glass, and then decided, okay, yes, I do like this. So it really functioned that way. Also, I do own 2 scopes. I got my first scope during COVID, and I bought it used. It was listed as very good plus. The box came and it rattled. Someone had thrown all the pieces inside the telescope in the tube. Fortunately, it did not hurt the mirror. I learned a lot rebuilding it, but I wanted something better because the stars move at night, you know? And so I did buy a Schmidt Cassigan with computer control. But with this, they do tell you you don't need a really good scope. And I found it easier to have my old rebuilt Newtonian in the garage. I would just pull it out and use that for most of the things through the different things you look for. And then some of the ones that got tougher, I then went to the motorized, so that the moon just stayed there and I could stare at it for a long time. But I felt I really learned a lot. And now I'm ready to do some more.
And what are you working on now?
Well, the second lunar one does appeal, but I really like binoculars. We go to Lake of the Woods every summer and I bring the telescope along. Takes up a third of the trunk of the car. And then the Canadian fires mean that there's nothing to see but the moon. But being able to, I think, just to go with binoculars is appealing. So So thanks for your help.
Well, congratulations. Fantastic. Great start.
Thanks. Thanks to Anton, if you're listening, and my wife, Anne Marie Rose, who put up with. I've got a schedule here from 7 to 9. Can we have dinner early or dinner late? And I did find that there's just a wealth of stuff online. I use the, what's it called? Clear Outside app, which lists the moon, the levels of clouds and all that, and then just planned it accordingly. So,
Fantastic. Congratulations.
well, thank you.
That's awesome.
Thanks.
Well done.
Thanks.
Well done. Keep it up. And now from the moon to the other thing that is somewhat easy to observe is Jack Shelton here. There he is. Fantastic. Jack has done a couple of things. The one that I'm going to be giving him tonight is the Sun Spotter certificate. Well done. Number 253. Congratulations. And you did not only just the Sun Spotter, but you did also some work with the eclipse. Is that correct? Did you talk about that last time?
No.
Would you talk a little bit about both of those? That'd be great. Thanks.
Hi, thank you, Jerry. I appreciate it. The eclipse, I didn't do much in the way of observing them, as far as writing down things or doing anything with, logging it or whatever, because I didn't really think about it until I got home and after I talked to you. But my wife and I used to live in San Antonio, and we knew the hill country pretty well, and that's where it happened to be for both the annular eclipse and for the total. And we did manage to make it to both of those. She is like, David, like your wife, mine is extremely nice to me about doing astronomy things. And so she went down, we enjoyed our anniversary down there with that, but we saw both of them. We got a chance to enjoy those. So, as far as the sun spotter, my first hack at doing any kind of sun spotting work was in the late 80s. That's when I learned about sunspot minima, because all my pictures were just circles with nothing in it. And I hadn't done solar since then. Mostly deep sky, mostly telescope work, but it was a beautiful spring and summer. And I thought, the sunspots are great right now. So I have an 80 millimeter, I have an 80 millimeter, Sky Watcher that I use for just carrying around and doing small stuff with. Bought a Herschel wedge and I was kind of blown away. So that's when I told you about my sketching. I had never sketched a darn thing in my life. I learned how to sketch. I don't sketch well. You see the sketches online that people do, they look like photos. That's not me. But
Start somewhere.
I'm not getting any better. So,
There we
but
go.
about 2.5 months or so with a 2-week break for an anniversary trip. It was good. I recommend it.
Well,
So thank you.
here's the pin.
Oh, okay.
Congratulations.
Thank you. I appreciate it.
Well done. Thank you. And so my last group, this is kind of an odd one. Do you remember a number of months ago, maybe it was a year ago, maybe it was a year and many months ago, I was complaining to the club about how we have so many people with the visual, that have done visual AL projects, but we didn't have a single imager who had done anything. And then we had one brave individual take the stand, and that you were the first one, which was fabulous, Doug. Well done. Congratulations. We now have another person here who I'm about to hand out 3 imagers. Tom, come on up. Tom Holman. And he's bringing his little friend with him, which is the little friend that he used to do all 3 of these. Let's give him some applause. This is kind of crazy. You have earned the Caldwell, the Messier, and the Bright Nebula, which for those of us who are visuals is really hard. And yet you've done all 3 with what?
With the CSAR S50. So
Crazy.
you can't do astronomy with this, but I have probably 600 or 700 images I've taken with this since I got it about a year ago. So Bright Nebula requires 100, and you can just barely see 100 in my environment. So I live in the city. I live just real close to here. So we got Bortle 8 or 9. So I've taken most of the images in this area. I had to go out for a couple of them that you really just couldn't see. But some of the images turned out okay. I like there's a one page on the Astronomical League observing that talks about imaging. It says there's kind of three reasons to do imaging. One is to be very artistic and come up with beautiful pictures, and you guys have done some really incredible pictures. And one is to advance science, and the other is to enhance your observing. So I kind of use this as a way to enhance my observing. So I've seen all these bright nebulas. I got all 110 Messier objects and then 70 of the Caldwell objects, which are difficult as well because a big chunk of those are in the southern hemisphere or right on the horizon. But I was able to get all of those, and they ran from about last March until about last November. You got to really figure out when they're going to be in the sky and plan out your day and find a bright, a cloudless night and all that kind of stuff to go look at it. But it's a lot of fun.
And these are the three, which is amazing. Here's the Caldwell and the Messier and the Bright Nebula. This one is the one. This one knocks my socks off because this is really a hard one. So congratulations.
Thank
Well
you.
done. Do you have any particular things that when you worked with this that was either a real advantage or a real disadvantage when it came to taking the images of these?
Well, the biggest advantage is when it's like 5 degrees outside, this sits out in front of your car and you sit in your car and you can just control it from there. But it's really fairly easy. You don't have to do an alignment, no polar alignment, no 3-star alignment. It has a GPS in it. It does live stacking. So you're taking the picture and you get a 10-second image and another one and another one. And on the really dim things that might take 40 frames, it just begins to show up on your tablet. And it's pretty cool because you can see it. And it's very accurate. So you go to the Sky Atlas, as long as it's got a level, as long as it's level and as long as you're there. And the object you're looking for is just right in the center of the screen. So you can kind of see it emerge and say, oh, there it is. That must be Caldwell 72, And so that's kind of cool. There's a built-in light pollution filter, which works really good for the nebula. You don't use it for the galaxies or the stars. But yeah, it's fairly easy. And yeah, Suresh. Well, one of the first things I imaged was Orion Nebula, and I got a picture of that on my phone, and it looks pretty good. The other ones don't look quite as good, but I like some of the Caldwell Nebula, like the Helix. It's just kind of cool to see, and it's kind of fun. I'm not a giant fan of globular clusters, and boy, you see a lot of those in the Messier. I'm so sorry, but after about your 40th globular cluster, you're like, okay, and then you have to describe them. Okay, it's a globular cluster. So anyway, but yeah.
But they're all different, aren't they?
Yes, they are.
They're all different.
Yeah. Anyway, so now I'm working on the lunar. I'm about one observation away from that one, and solar system, which is kind of cool, and foundations of imaging.
Well done.
All right, thank you very much, guys. Jerry, you have one more thing to say.
Get out there and observe or image.
All right. Thanks. So we've got a quick presentation from the North Central Region Astronomical League. They are planning their convention here coming up, and you'll hear a little bit about it. So, all right.
All right, thanks, Pauls. Yeah, I'm going to talk about the NCRAL 25 convention.
Forward that.
Thank you. My name is Randy Heeman. I'm president of the Rochester Astronomy Club. With me tonight is John Adewell with his raised hand here. He's VP of our club, and he's also the regional representative to the Astronomical League for our region here. And Al Schiedler might be on the Zoom call too. So he's currently chair of NCRAL this past year and doing a great job. So I'm going to try to speed through these slides here. You can see our logo, First Light, New Frontiers, New People. I'll explain that as we go. But first I'm going to run through the what, where, when, what, why, and we'll jump into that right now. So just as a little refresher for all of you, there are 10 regions of the Astronomical League. We have the North Central region there. And in the past few years, as we go through, a lot of the NCRL annual conventions have been more towards the eastern shoreboard over there, and not many in the central or the western areas, although you guys put on a great Alcon 2018. The three of us were there, I believe, for that, and that was a lot of fun. Rochester put on a couple NCRALs in the mid-20 teens. And going forward here, we have in 26 Cedar Rapids doing the convention, and we're trying to twist the arm for Milwaukee to do the 27 convention. But what we do not have is any takers for this year, 2025. So the executive committee commissioned an ad hoc committee to independently see if they could pull it off for this year. So this committee has waxed and waned with its membership. This is the current membership right now. John and I are trying to chair it, and we're getting a lot of people. We've had some key people leave the committee, so we coerced and some of our own club members to fill in some key spots over the past couple months. But we're getting through it here. We wanted to have the meeting more westward if we could, and since we're doing all of our meetings by Zoom, we thought we need to play it safe and find a larger metropolitan area. So we ended up thinking, and we had committee members who had relations with your society here, so we ended up looking at Minneapolis, St. Paul. We ended up with the best deal offered to us at the Marriott Southwest, so that will be our anchor location. And of course, somebody came up with the idea that your beautiful Eagle Lake Observatory would be a good place for that Friday, more informal session there. So that's where we're going to be. The when is April 25th, 26th. There might be some activities on Sunday, but mostly everything's going to occur on that Friday and Saturday. We tried to avoid the holidays. I think Astronomy Day is the 3rd, 4th. It's the next weeks we're avoiding that too. What we couldn't avoid is World Penguin Day and Pretzel Day. So all of you that are going to celebrate that, we'll miss you, but I hope a lot of the rest of you can kind of join us at the convention there. So there we are. Now we're doing something at ELO in late April, weather dependent. We'll have to see what we can pull off, but we do have one of your members giving tours. We'll have some tasting and some talks and some tours. And we're getting everything organized for that. We'll see how the weather cooperates at that time of the year. Then the main event on Saturday, we're going to move that business meeting to the morning instead of late afternoon. Run a slate of presentations, and then the banquet meal, keynote speaker, and all those other activities you see on the slide there. We've already got our slate of speakers. We've urged them to try to do present new frontiers, so newest, latest, greatest, innovative things that are going on in their world, or if they have some existing talks, to modify it to bring it up to date as much as they can. Got a couple alternates if we need them going through there. We're trying to work on our sponsors and vendors to help support the event, and we got a lot of work to do there yet. And lastly, the why. We want you there. We want you to want to be there. I like Venn diagrams, so this is kind of a half-hearted, but very seriously, we want people to be there for our first light, bringing new people, hopefully from the West a little bit, and looking at those new frontiers. But more seriously, we do want people to be there. What we do, we're amateur astronomers. What we do is we learn and we share. That's what we do. And it's a good time to, as we're doing tonight, kind of enjoy the camaraderie, meeting new people and some old people you haven't seen for a while. Now, at the Marriott, we cap out at 90. That's what we safely went with. Typical meetings will be about the size of this meeting. About 45 to 75 will attend these NCRALs. It might be harder travel for those in the East, but we hope a lot of you show interest in it. And we have some connections and maybe get some people out in the Dakotas, because they have clubs, and you don't have to be in a club. You don't have to be part of the NCRAL to come to this meeting. And so we're going to reach out and have some campaigns to get those people involved too. And that's it. Questions, I can wait till the end of
No, go ahead,
Dave's
go ahead.
presentation, but if anybody has any quick questions, I can take them now. John can answer too. Yeah.
Correct.
I do have some questions about ELO getting that shelter reserved, that beachfront one, I believe. We do have somebody volunteer for, okay. And Ahmed will be our liaison with some of those details we know we have to figure out before it happens.
I'd like to add that we'd really like to get some volunteers from MAS. Ahmed is, I think, the only member from MAS that's on our committee. We've got people that have already been doing a lot of the heavy lifting. There's some nice things to do. We have a meeting once every 2 weeks, Monday night, 7 to 8 on Zoom for a planning committee. But so we don't have really heavy chores or a lot of hours involved, but we sure would like to see some active participation from your group. One other thing I'd like to add is too, we are going to have a website for registration and information.
Yeah.
We're not going to stand it up until the end of January. So you probably won't see it if you search for it. Oh, I'm sorry.
Don't repeat it all, just.
Okay. So that's it.
We really do appreciate you being part of the conduit to make this happen. And hopefully we have more conversations now that we're in this part, 4 months into it, getting closer to the convention.
All right, thank you. Thank you, Ray. Thank you. All right, roller scopes, Antone, really, really quickly, because we're cutting into Dave's time here. So it's all in one slide.
Okay, oh, yeah, so it is all in one slide. All right. We, as already mentioned, we do have our loaner scope program. We have 19 instruments, refractors, Dobbs, cassegrains, binoculars, and a solar scope. We had 85 loans this past year. Anyway, there's pictures of what we have. Members who are interested in borrowing one of these, and there's no cost if you're a member, go on the website. There's a big box right on the home page that will take you to a list of the telescopes. You simply select your first, second, and third choice. I will get the email, and then as was mentioned earlier, we make an arrangement for you to come stop by my house and pick it up. It's yours to use for 30 days, and then just return it in good condition. We also have DVDs. In fact, I have a couple of requests for those right now. Questions?
Thanks, Antone. Oh, one question.
Days just never seems like enough to me. Can we push it out to 90 days? 30 days is never enough. I mean, in Minnesota, we might not even have a clear sky in a 30-day period.
I mean, quite often, and correct me if I'm wrong, Antone, you can get more than 30 days. You can extend it, so if
Yeah.
it's available.
The policy allows one additional month, as long as no one else has requested that telescope. And now that we have 19 instruments, that often happens.
All right, weekly happenings. So it comes out every Tuesday. If you need any announcements, please send a secretary to our secretary Claire at secretary@mnastro.org. And if you need to subscribe from the homepage, you can fill out that form and subscribe and get that MailChimp blog every week. Okay, online communities, I'm just going to mention quickly. Membership includes Slack access. We've got the MNastro forums, the website, the YouTube channel, and the social media. So follow us on all of those platforms. Official mass stuff available, Cafe Press as usual. Everything is there. And one thing I want to talk about a little bit is logos. We talked about logos a little bit last month. There is an initiative to upgrade our logos in terms of higher resolution, more options. So there is an open channel on the Slack called for logo discussion. So please chime in on some of the proposed logos that we have gotten. Gemini is our newsletter. Please, Father Brown only accepts original articles, all generated internally from MAS. We don't publish anything from the outside. So please read the Gemini and contribute. Another way to contribute. All right, public service announcements. Already talked about the logo. Really, really quick. Steve here has a quick public service announcement. And Dave, if you want to get ready for your talk.
Yeah, just a quick announcement that there's another group of people, folks around this region that looks to the stars and explore the skies. And that is the 1965 started Twin City Meteorological Society. Much less than a tenth of the membership of this group, and which is good because I'm the treasurer and a board member and much easier to maintain. But we're presenting in this room on January 30th, Thursday, from 6 to 9 o'clock in the evening, free to everybody, don't have to be a member. But it'll be the 4th annual Minnesota State of the Climate presentation. And just to name a few, Kenny Blumenfield, it's in conjunction with the Minnesota DNR. Kenny Blumenfield, Pete Boulay, Michelle McGrath, Coco Ross, the climate, discussing the 5 most important weather events from 2024 and further discussions as well. So free here, January 30th.
All right, thanks, Steve. And I don't want to cut into Dave's time anymore. So our featured speaker is Mr. Dave Falkner.
All right. This is hot. Can you hear me now? Oh, yeah. There you go. Thank you, everybody. You're killing me. Getting me only 45 minutes here, but we're going to try and get through this anyway. Bear with me on this. So we're going to talk about the cosmic distance ladder, or how you measure distances in space. Not as easy as it sounds. I want to, first of all, kind of set the scene here. First of all, I'm going to just introduce the better known methods. There are a number of methods that they're using today to estimate distances. I'm going to just introduce some of the better known ones. I'm not going to dive into the weeds. We're not going to go into, special relativity and, all these equations and stuff like that. I'm just going to tell you the concepts, and hopefully you'll be able to understand what's going on. And I am trying to speak to all levels of knowledge, because I understand there are some people here who may know a lot about the distance ladder. In fact, one member sent me his 10-page term paper on Seaford variables for this, which I thought was very nice. It's a nice paper, good job. But I am going to try and speak to all levels so that people who aren't familiar with the distance ladder will also understand what's going on. Okay. Interestingly enough, when Ahmed suggested this, I said, yeah, I seem to have done some things on the cosmic distance ladder. Couldn't exactly remember what I was doing, but then I realized that I wrote a book, and quite a bit of the book is actually on the distance ladder. I happen to have 5 copies with me tonight. So if you're interested in digging in deeper in this, let me know. I have copies of my book back there at $25 per copy. Okay, so moving right along, we're going to start with stellar magnitude, because we're going to find out that stellar magnitude is a very important concept here as we go moving through. It was first introduced, I suppose, a number of civilizations had their way of measuring star brightness, but we talk about Hipparchus and Ptolemy, who originated it. And the way that they figured it out, they said, well, we're going to make planets magnitude 1, and then we're going to have the faintest objects at magnitude 6. And between one brightness to another, about 2.5, about twice. So in other words, magnitude 2 to magnitude 3, magnitude 3 is twice as faint as magnitude 2. Okay, it's kind of counterintuitive, because the magnitude scale increases with the faintness of the object itself. So, and obviously then you can go into negative magnitudes, right? Because there's things that are a lot brighter than planets in the sky. And so that was a little bit problematic, because it was kind of subjective in the way that it did. So we wanted to try and standardize that. And that didn't really happen until about 1865, when Norman Pogson formalized the scale. Now we're talking about what we call apparent magnitude. This is the visual magnitude that we actually see with our eyes. Okay, it's represented by a small letter m, which become a little more apparent as to why, what that's used for. And then Pogson, he formalized it by saying that the brightest magnitude star, the first magnitude star, we're gonna standardize that, and then from first magnitude to 6th magnitude is a factor of 100. Okay, so and then each magnitude, it would be like 100 to the 1/5, or about 2.5 times brighter. Okay, now originally they were going to use Polaris as a magnitude star and use that as the standard. until they discovered that Polaris is actually a variable star, so that doesn't really work as a standard. So they went to Vega instead and used Vega as magnitude 0. Since then, they've even gone beyond that because they wanted to have something that wasn't, just an object. And so they kind of averaged the magnitude 0 stars to get what true magnitude 0 is. When you do that, Vega turns out to be about magnitude 0.03, but that's close enough for us. It's magnitude 0. We start with that, and then we move down the scale. Here you have a list of several objects and their magnitudes. So you see magnitude negative 27 for the sun because it's pretty bright. And then you have these other objects here. The eye limitation is magnitude 6 for most people. That would be under a very dark, clear sky, no moon, relatively low humidity. I mean, you have to have really ideal conditions to see magnitude 6 stuff. Okay. Right. So that's apparent magnitude or visual magnitude. Now let's talk about finding distance by trigonometry or triangulation, because they did this, and we'll talk about that in a minute. So if you have this setup here, where you're trying to find the distance to the boat, you have, distance from A to B, you can measure that out. You know how long that is. And then you measure the angle from B to the boat and A to the boat. And then through trigonometry, you can calculate what the distance D is to that boat. Okay? Trust me on that, it works. All right. So we do something similar in astronomy. It's called parallax. And parallax is pretty easy to understand. If you put your finger out in front of you and you look at with one eye and you notice what's behind the finger, and then you shift to the other eye, it looks like the finger has actually moved over. Okay. Same thing with stars. If you go out and you look at a star and you use the Earth's orbit as a baseline, as the Earth goes around, that star will move against the background stars. Not much. So it's very, very small. And so we'll talk a little bit about that. Okay. But that distance from the Earth to the sun is something that you need to know. And we call that now the astronomical unit. And it's the mean distance between the Earth and the sun. And beginning with the Greeks, they tried to figure out, well, how far is it to the moon? And how far is it to the sun? And so what they did was they first tried to figure out how big the Earth is. Okay. And while there were some flat earthers out there who tried to do it that way, their estimates were way off, obviously. But even with the round Earth, and they tried to figure out what the radius of the Earth was, they had some success in getting a value. But quite frankly, measuring the distance from the Earth to the moon and the Earth to the sun for them was very difficult. And they did an Earth radii and was off quite a bit for both values, until you get to about the mid 1600s. By that time, we now are we have telescopes to use, and the instrumentation is getting much, much better. And so they finally had a reliable value for the radius of the Earth. And during the parallax of Mars in 1672, they were able to use parallax from Paris and from French Guiana to measure that. And they got a solar parallax from that of about 9.5 minutes, and then an astronomical value, an AU value of about 22,000 Earth radii. Okay. And then they further refined that with the Venus transits in the 1700s and the 1800s, and yielded a parallax measurement within 0.1%. So they're getting pretty close then. So the term the astronomical unit wasn't actually used until 1903. But after that, the current value, about 23,455 Earth radii, or those distances that you see there, generally used as a unit of measure within planetary systems, not just our planetary system, but exoplanets as well. The stellar planetary systems that we hear about, they'll measure the distances in terms of astronomical units, mainly because it's pretty long without being really long. Okay, we start talking about some of the other units we're going to talk about, and they're much more suited for stellar and interstellar and intergalactic measurements. Okay, and then of course, now we have means, if you know the astronomical unit, and we can use trigonometry again to say measure Venus at greatest elongation. It's a right triangle from our sun to Earth and through Venus. And we can use trigonometry to calculate what the distance is from the sun to Venus by using that. About 0.75 astronomical units, if you want to know. Okay, so there's that. As Johann Kepler was figuring the orbits around the sun and the speed of the planets and the like, one thing they discovered was that the force of gravity seemed to decrease as the square of the distance, and they could show that from their calculations. And Johann Kepler decided that, you know, we could also show that light that light behaves the same way. That as you get away from a source of the light, it dims by the square of the distance. And so we could calculate the distance to something by knowing what the source brightness is and what the brightness is at that distance, and then be able to do that calculation. So when we're going to talk about absolute magnitude, which is that source magnitude, I'm going to get something here real quick. So luminosity is the intrinsic brightness of an object, okay? And we take the intrinsic brightness and we figure out how bright that object's going to be at a distance of 10 parsecs. And I'll explain what a parsec is in a little bit. But that way we have a standard distance that we're going to measure the brightness of an object, the absolute, the intrinsic brightness of the object. I have here some examples here for, like, if we take our sun and move it to 10 parsecs, it would be at a magnitude 4.83. We have Deneb, Betelgeuse, either -5, -8. A GRB that's a gamma ray burst that occurred, and it was at -38 magnitude. That would seem like 20 quadrillion times bright as the sun when seen from the Earth. That is huge. Okay, but its symbol is the capital M, and we'll use that in our equation. And that's, but it represents the brightness of the object if it were placed at 10 parsecs. So now we have the thing called the distance modulus, and this is the equation that's used by astronomers. And it's, if we take the absolute, the apparent brightness, the apparent magnitude of what we see, subtract what the absolute magnitude is, and then we use the 5 log 10, and R is the distance in parsecs to that object. Okay, and that's the formula that's used. And if we know 2 of the 3 parameters, we can figure out the other one. Okay, and this turns out to be a very powerful tool, and we'll see why as we move along. Okay, now I mentioned parsec, and so what is a parsec? Well, as we look at objects in the sky, it's like a sphere above us, right? And we measure things in degrees. So for instance, from the horizon to the point overhead is 90 degrees. And then all the way around us to be 360 degrees. Okay. And the separation of 2 objects in the sky, we measure in degrees. And then degrees are further broken down like time. So like there's 60 arc minutes to 1 degree. And there's 60 arc seconds to 1 arc minute, and so forth. Okay. So that's how we break down that. So what a parsec is a parallax of the Earth-Sun distance, 1 astronomical unit. That, how far away would you have to get in order for that separation to be 1 arc second? And it turns out it's about 206,265 astronomical units away. And it's the same as about 3.26 light years. We haven't talked about the light year yet, but we will. Okay, so that's what a parsec is, and that parsec is a convenient unit to work with when you talk about interstellar and intergalactic distances, because it's much farther, much longer. Okay, so When we measure parallax, turns out that it's relatively simple to do if you can get the measurement. Okay, we use the astronomical unit for one side of a triangle, and then we measure the angle, the parallax angle P there, which is right here, right? Oh, you can't see. Oh, there it is. Yeah, so you can measure P here, the parallax angle. We have the astronomical unit here, and R is the distance to the object. And then it's R equals 1 over P. And it turns out that if you look at Sirius and you get the parallax angle of Sirius, turns out to be 379.21 milli arc seconds. That's really, really small. But you plug it into the formula and it gives you about 2.637 parsecs, or about 8.6 light years, which is how far Sirius is away from us. Okay. Obviously, stellar parallaxes are incredibly small, and they really weren't able to be measured until the telescope and instrumentation got fine enough. The first person to do that was Thomas Henderson. He did it from the observatory in Cape Town, South Africa, measuring the parallax of Alpha Centauri, which is the closest star after our sun. And he was able to do that. He measured it and got about 200,000 astronomical units, or about 3.16 light years. The actual value is 4.29, I think, or something like that. So it was relatively close. He did a pretty good job on that. Now, so there's limiting factors on Earth to being able to find the parallaxes. One is the size of your telescope, obviously. And the second one is the atmosphere, because the atmosphere distorts the light as it comes through. And so it gets hard to be able to measure parallaxes out very far, because you can't, the atmospheric distortion. Space-based telescopes, on the other hand, can get very, very good. And so we have Hipparchus, which has been out there, and it could measure down to 1 milli arc second, a few hundred parsecs that it can measure stars away. Hubble got down to 30 to 40 micro arc seconds, and was able to get parallaxes to measure star distances out to about 5,000 parsecs, or 16,000 light years. Now we have Gaia out there. Gaia has the capability of measuring down to 7 micro arc seconds for magnitudes of up to 12th magnitude, 27 micro arc seconds for magnitudes up to 15th magnitude. I couldn't get a reading on how far out that is, but it's pretty good distance within our galaxy. And it's measured the parallax of over 1 billion stars. So we've got a lot of good parallaxes to work with. And parallax, measuring distances that way, is the most accurate way to measure the distance to a star. And we're going to see where that's going to help us in verifying some of these other methods that we're going to be talking about as we move forward. I haven't talked about the light year, but it was first discovered by Ole Romer. He was measuring the orbits of Jupiter's moons and found that they were shorter when the Earth was approaching them and longer when the Earth was receding from them. And he was able to calculate the time that light took to travel from Jupiter to the Earth as about 22 minutes, which was close, but it's 34 minutes actually, but okay, but that's the idea. There's a couple other methods here. I'm not going to go into them a lot, but there have been several different ways that they've been able to measure the speed of light. So a light year now was first introduced in 1851. It was a term that really wasn't well accepted at first, because it sounded like a value for time, not for distance. But it kind of stuck. And today we know that as the distance that light travels in a year, a Julian year. That's about 5.88 trillion miles. Okay. All right, so here's what we've talked about: astronomical unit, the light year, and the parsec. Okay, so far so good. The challenge, as I've mentioned before, is determining m. That's the challenge. If you can get what the absolute magnitude is of an object, then the distance comes out pretty easily. Okay. The invention of spectroscopy and astrophotography really aided us in being able to do that. since Newton's time, they've been able to pass sunlight through a prism and see the spectrum of light that comes out from that. But later on, and as they were able to spread that spectrum out more and more, in 1814, Joseph Fraunhofer discovered that within that spectrum, there were these black lines. And so he drew that because the photography hadn't really gotten into it yet. So he drew a picture of what he saw. And he didn't know what the black lines were. He just knew that they were there. Okay. And then astrophotography started developing in the 1800s. And by the mid 1800s, they had finally developed a fairly decent way of taking images on glass and developing those. And so they had these glass plate images. And one of the people who was really a forerunner in this was this man right here, who's Henry Draper. Henry Draper had an 11-inch telescope that he used and was able to put a camera on the back of that and start taking astrophotographs with that, and got to be pretty good at it. And then he went and put a diffraction grating on the front of that to be able to actually capture an image of a spectrum of a star. And he captured literally thousands of images of stars on glass plates. So he had all those. Henry Draper and his wife Anna were good friends with Edward Pickering, who we're going to introduce in just a minute. And when Henry Draper passed away, Anna Draper didn't know what to do with all these thousands of glass plates of images, so she donated that to the Harvard Observatory, which was where Pickering was. For a spectral line, what was found out was that these black lines really do mean something. Between 1850 and 1860, Gustav Kirchhoff and Robert Bunsen discovered that each element had a unique set of lines associated with it. You can see them here from helium on down. And then in 1859, Sir William Huggins figured out that if you could take those individual lines, you can superimpose them onto the spectrum of the sun and be able to figure out what the elements were that were composed of the spectrum on the sun. And so that's how they figured out, okay, these lines mean something. They mean that these are the elements that are present in the spectrograph, okay? So now we have Edward Pickering, who became the director of the Harvard Observatory, and he was having his graduate students pour over these glass plates to analyze them, and found them that they weren't really doing a very good job. And he was coaxed into hiring his housekeeper, Wilhelmina Fleming, to come in and do some analysis. And she did a much better job than any of the graduate students. And so he wound up hiring college-educated women and paying them a pretty good wage at that time to come in and analyze all these glass plates. And so that's what they did, and made a number of great discoveries we're going to see here in just a few minutes. Okay. With this idea that we have all these spectrums, these lines, the stars had different sets of lines. And when you look at one star and another star, the lines weren't all the same, they were different. And so they started, not the computers, but astronomers in general, started categorizing these things. And there are several attempts to categorize the stars. And one of the people who was fairly good at this, it turned out, was Father Angelo Secchi, who made a first attempt at classifying stars by their spectrum. Okay, he had 4 separate classifications you can see here. Pickering and his computers thought that, that's fine, except that it's too broad. They needed to fine tune that and break that down into a more refined classification. And they made a couple of attempts at that as well. But eventually Annie Jump Cannon was able to put together her classification of stars, P for planetary, and then the O stars were the brightest stars with their spectrums, and then the B, A, F, and so on and so forth, down to M stars, which are more of the red dwarf stars. The R stars were carbon stars, and N stars were like carbon stars, but they had more blue in them, and Pickering thought they needed to have a separate classification. Okay, so then in the early 1900s, Anjar Hertzsprung in Copenhagen and Henry Russell in Princeton independently figured out, hey, we can plot these star classifications and come up with this diagram that plots luminosity against stellar color, the Hertzsprung-Russell diagram. And so we all seen this before, where this line here represents the main sequence. This is where our stars are still burning hydrogen in their core. And then as they use up the hydrogen, they begin to break off into other areas here. Okay. So now we have kind of a rough way of being able to determine magnitude, but it's pretty broad here. There's no real specifics in here. All right. So we're still looking for a good way of judging distances using absolute magnitude and, of course, the visual magnitude using the distance formula. So the next thing we're going to do is talk about John Goodrich and a couple friends of his in 1784 were looking at variable stars and saw a star that had this type of pattern in its variability. One of the stars was the Cephid, Delta Cephus, and that's what this star was. So this pattern of variability, this variable star, was named after the Cephid variable. And there are a number of these around the sky, and they have a very distinct pattern to them. They're also quite bright, and that variability is rather quick too. It could matter of days to just a few weeks that you can measure the total variance of the star. Well, one of the Harvard computers was doing an analysis of variable stars in the Magellanic Clouds and found that there are about 25 stars that she found in the Magellanic Clouds that were Cephid variables. But she also noticed that the brightness of those stars seemed to correlate with the period of the variability. And so she was able to plot that. And there's the plot of it, and you can see where it follows. And so you can actually determine what the absolute magnitude of the Cephid variable was by the period of the variability. Okay, and so that was huge. And so now they had a star where they could actually know what the absolute magnitude was just by the variability of it for Cephid variables. There was some discrepancies on that, and it turned out that in the 1940s, Walter Bade just recognized that there are actually two different classifications of Cephid variables. They both behave the same way in that you could determine the absolute magnitude from the period of the variability, but from the spectrum, you can determine whether it was a type 1 or a type 2 variable, type 2 Cephid, and therefore be able to determine exactly what the absolute magnitude was. But the nice thing about this is what these were bright, so you could see them. They were good stars farther away. Now we're going to fast forward to 1920. Well, actually back up a little bit, just to 1920. In the 1920s, the astronomers believed that the extent of the universe was the Milky Way galaxy. That was the extent of the universe. But there was some discussions about what they called spiral nebula. The spiral nebula they saw within, in the night sky, and some thought that it was part of the Milky Way galaxies. Others thought that they might be outside of the Milky Way galaxy. And there's a big debate in 1920 between Heber Curtis and Harlow Shapley. Harlow Shapley and Heber Curtis, the great debate about whether or not these were in the Milky Way galaxy or not. That didn't really resolve anything, but at the same time, the giant 100-inch telescope was being built on Mount Wilson, the largest telescope in the world, a full 2.5 meters. Not very big these days, but anyway, but it was big enough back then to be able to see individual stars in the Andromeda Nebula. And so our good friend Edwin Hubble was in charge of that observatory, and he was taking images and looking at the Andromeda Galaxy and found, oh my gosh, there's a variable star there, and it's a Cephid variable. we know what the absolute magnitude of it is. Now, they thought that the Milky Way galaxy was about 200,000 light years across, but when he did his calculation with that Cepheid variable, he found that it was about 1.5 million light years away, clearly outside of the Milky Way galaxy. And so now all of a sudden, the universe has expanded a little bit. And Cepheid variables were bright enough to be able to see not just in the Andromeda galaxy, but several other local galaxies that we have. And so this is one of the first things that actually got us to go outside of the Milky Way and realize that the universe is bigger than that. Another variable star that was discovered was the R.R. Lyrae variable star. And Wilhelmina Fleming was another person in the Harvard computers who looked at the absolute magnitude of R.R. Lyrae the variable stars and realized that those could be used as standard candles as well. It was really nice because its absolute magnitude didn't depend on the length of the variability. And she was looking at globular clusters. So we find that Cepheid variables are well, they had two different categories, but the R.R. Lyrae ones were found as globular clusters and were generally older stars. And they had that characteristic curve that you could find, and they had an absolute magnitude around 7.2, so they knew how much that was too. They could use those types of stars for measuring distance as well. Okay, so that did well. And then now we got to talk about some supernova here. Supernovas are, when they go off, they're brighter than a whole galaxy. So you can see them in galaxies very, very far away. There are two types. There's type 1 and type 2. The type 2 is the one where you have a massive star where it uses up all its fuel, the core collapses, and there's a massive explosion. That's the Crab Nebula. Usually leaves behind a neutron star or a black hole. And so that's great, but we don't care about that. We care about type 1 supernovas are what we're interested in, specifically type 1a. Type 1 supernovas occur when a white dwarf is orbiting a companion star and begins drawing off material from that star from its gravity. And that collects on the surface of the white dwarf until it gets to a certain point where spontaneous fusion occurs and it explodes. And in the difference in the spectrum, the difference is that you will find hydrogen in a type 2, but you'll find no hydrogen in a type 1 supernova. Furthermore, a type 1a supernova has a strong silicon absorption line. So we can actually see a type 1a supernova. Two guys who were really big on this were Subrahmanyan Chandrasekhar. He was an astronomer in India. He was a specialist in stellar evolution and supernovas. And Mark Phillips, who's actually still alive, who's a little older than me, but he worked, his career, most of his career was down at the Los Campanas Observatory in Chile, and he was part of the supernova survey. Okay, and what Chandrasekhar discovered was that once that white dwarf pulls in enough material to equal about 1.44 solar masses, which is the mass of our sun, 1.44 times that, then the pressures and the temperatures are high enough that this spontaneous fusion will occur and the star will explode. White dwarfs in general are about the same size, so the amount of material that has to gather for 1.44 solar masses is fairly consistent, and so it is typically measured at an absolute magnitude of minus 19.3. What Phillips did was he actually was computing what the magnitude of a type 1a supernova would be based on the curve, the light curve coming down. And after 15 days, you could calculate what the absolute brightness of the type 1a supernova was from this curve that he had. And he could verify that, yes, in fact, you could use this as a standard candle at minus 19.3. This was huge because, as I mentioned, the type 1a supernova is as bright as the galaxy, so now you're able to measure distances much farther out. I want to state that the Cepheid variables, R.R. Lyrae variables, and even the type 1a supernovas could be verified with parallax measurements, so that's kind of how they were able to verify those. The next one I want to talk about is a more specific type of measurement. When you have a huge cluster of galaxies, the amount of gravity that's associated with those galaxies will actually bend space and time. Okay, and so if an object is behind that cluster of galaxies, the light will bend around those galaxies, and then what we see is this picture here, where you have the cluster of galaxies in the center, and these are actually 4 images of a quasar that's behind that galaxy. Now, quasars are highly variable objects. So what they're able to do, excuse me, is time that variability. Excuse me. Time that variability, and each image has a time delay. And they're able to measure that difference in time, and then use the lens model for the gravitational lensing and general relativity to calculate the time delay distance, how far that quasar is based on those time delays of light going around the cluster of galaxies. And this is called time delay cosmography. And that's the extent that I know about that. So, okay. Finally, let's talk about the one that everybody's been waiting for, I'm sure. When we talk about the Doppler effect, it was Christian Doppler who first proposed that sound waves for a source that's coming towards you get compressed and the pitch goes up, and when it passes by you, the pitch drops because the sound waves are then expanded out. Okay, and then they knew at that time that light was also a wave, and so he conjectured that as a source of light comes towards you, that the waves be compressed and that would get higher pitched, in other words, get more blue, and then as it passed you, that the light waves would be stretched out and would get more red. Okay, and so from that he surmised that all stars were white and that the blue stars were coming towards you and that the red stars are moving away from you. Makes logic sense. Totally wrong, but logic sense. Okay, so but in 1848, though, H. Fizeau theorized that spectral lines would move as a result of the stellar resource, and that's what's really happening, is that the spectral lines will move based on whether the source is coming towards you or going away from you, and that was able to be verified. So we see here where we have this is the at-rest spectrum. When it's coming towards you, it gets shifted toward the blue a little bit. If it's moving away from you, it gets shifted toward the red. Okay. Now, Edwin Hubble, when he started studying galaxies, found out that outside of our local group of galaxies are all moving away from us. They all have a redshift. Furthermore, the farther away a galaxy was, the more the redshift. So the velocity increased with distance. And you could actually be able to measure the redshift and be able to figure out how far away the galaxy was based on the redshift. Okay, it's a simple calculation, and it turns out while z itself is dimensionless, okay, you just do the calculation. That graph you see there is the redshift, the z line, if you would, as you move out, as you get to more redshift. The other lines, clusters in there, are verification of that from observations from the Hubble telescope and ground-based using parallax and other techniques. So turns out this redshift is actually pretty accurate. Okay, so here's a Hubble image showing a number of objects that have redshifts: 11.9, 8.8, 9.5, 8.8, and so on and so forth. Okay. And if we so this is the value of z and how far away objects are. Now, keep in mind that let's take an object that has a z value of 5. It's 12.4 billion years that the light's been traveling. So it's about 12.46 billion light years away. However, all that time the light's been coming toward us, the universe keeps expanding. So that today, that is actually at 22.3 billion light years from the expansion. So that's based on Hubble's calculations of how fast the universe is expanding. Now, he made this whole formula about the expanding universe, and he had to make an assumption. An assumption is that the universe isn't bending or twisting in a weird way, that it's kind of a flat, and it's just expanding out in a flat way. Okay, so there's this expansion formula that he put together, and it's really, again, it condenses down to the velocity that an object is moving away from you is based on its distance, d, and the Hubble constant, which is interesting. It's a constant at a particular point in time. When you move the time, the constant changes, which is kind of weird, but that's it. But if you're talking about 100 years, astronomically speaking, that's a moment in time. Okay, it's very close. So and there's a couple ways of measuring this. You could use the direct method for those for those galaxies that are close enough to you. You can use Cepheid variables or type 1a supernova and be able to measure the distance from that and the R value and be able to verify the Hubble constant there. And then the indirect method is analyzing the cosmic microwave background, which is kind of this background noise left over from the Big Bang. And they have ways of being able to calculate how fast things are expanding in the greater cosmological aspect of it. Okay. The problem that comes up is that when you use those two methods, the local method and the CFB-based method, you get two different values for the Hubble constant. Okay. The local gets you about 73 kilometers per second per megaparsec. That's the units that is. And with CMB based, it's 67 kilometers per second per megaparsec. And this difference in values is what they call the Hubble tension. Okay, it should be the same for both, but it's not. And why isn't it? They don't know. Man, that's what we're still looking at. But it could be due to a number of things. It could be the measurement methods they're actually using. It could be the instruments are out. Very likely, it's more than that, though. It's probably, in my opinion, two different things. One is that the physics in the early universe may actually have been a little bit different than the physics that we have today. Don't know that, but it's possible. We got to figure that out. Probably the bigger reason is dark energy and dark matter. We can see the effects of those, but we don't know what it is. And until we figure out what those are, we probably will never be able to solve the Hubble tension. I don't think. So there's that. And then just a couple mention of a couple more distance measuring things we use. One is planetary nebula luminosity function. George Jacobi was able to correlate planetary nebula masses to their luminosity in the O3 part of the spectrum. So this is very specific to O3, but the brightest nebula have an absolute magnitude that can be used for calculating distances in the O3 part of the spectrum, and you can see those in other galaxies. And then the Tully-Fisher relationship has to do with how fast the rate at which a spiral galaxy is turning is related to its mass, and that's related to its luminosity. And so you can correlate luminosity to the mass of that galaxy based on its rotational speed. And so they use that. Here is kind of the distance ladder in a nutshell. And you can see there's many, many, many different methods that are used. I talk about a number of these in my book. I don't get real into the weeds, but you know, there's also the stories of the astronomers that discovered some of these things too. So, made it. Again, any questions? Sure. Let's get a microphone.
Can you back up one slide and let us stare at that while questions?
Absolutely.
Thank you.
John here. Well, okay.
Oh.
Alan?
Real quick, parallax is at the bottom of that because parallax is what allowed them to establish the Cepheid variable distances to begin with, right?
Right.
Yeah. So yeah, parallax, I didn't see it on your chart there.
Yeah, yeah, okay, yeah.
So you showed a photograph of 4 quasars
Yeah,
around a galaxy cluster. Is that called the Einstein cross?
yes, that's
Oh.
the Einstein cross.
Okay, cool.
Absolutely correct.
So before like circa 1800, obviously it sounds like magnitudes date back a very long ways. Did they have any way of measuring the magnitude other than just kind of eyeballing it?
Not really, because one of the reasons we were able to standardize the magnitude scale was through photography and photometry. So now you can use you have a standard and you can keep that standard. Otherwise, to your point, it was pretty subjective, in terms of how bright a star was. Well, I think it's this bright. Well, I think it's this bright. So when you have photography, astrophotography, then you can get to the photometry value of it.
Dave, one question I had is on redshift. Wouldn't redshift be affected by dust and gas in between?
They do have to account for that, yes.
Okay, I was wondering.
Yes. Like I said, I didn't get down to the weeds, but yes, they do have to account for that.
Any other questions? Online? No? Thank you, Dave. You made up for it. You made up time.
You made up time.
So we will be going to Pizza Luce, or a number of us. So please join us at Pizza Luce if you're interested. Next meeting is the first Thursday of February, February 6th at 7 p.m. right here at the Anbetu Techa Center. And online, of course. So again, meet up at Pizza Luce. See you next month. Thanks.